Right. Thank you, Jen. Yeah, hi. My name is Chris Lamb, and yeah, I'm a fifth year grad student at the University of Florida, where I work with Professor Sarah Ballard. But I'm going to talk about a project I did a few years ago as a pre-doc at the Center for Computational Astrophysics, working with Megan Bedell and Lily Zhao on Gaspery, which is a software written to optimize the scheduling of RV follow-up observations of active host stars. Um, I've thrown in some pretty pictures from the paper that we wrote for Gaspery. Um, they're just there because they're pretty. I will explain them later. Okay, so like any good exoplanet talk, I'm gonna start by saying we have found thousands of planets with Kepler and TESS. And then I will also say that follow-up for characterization continues to be a precious resource. Um, so yeah, backing up one step, why do we want planet masses? From this figure from Bonomo et al. 2019, um, if say you from a transit survey you know that the radius is like two Earth radii, then without knowing the mass, that planet could be could lie on one of many of these contours, and so in order to get at the least the bulk composition, we want mass, and we want mass to some reasonable level of precision. And also, if we want to be tautological, we said we would do it, so we should do it. So why is it hard to get masses? In a word, in two words, stellar variability. So this is an example, like a simulated light curve or RV time series for AU B, and not every star is going to be like this canonical noisy star. But to illustrate this, like you've got your stellar signal with an amplitude of like 50 meters per second. You've got the planet signal at 5 times smaller than that. And so I've used the GP to simulate what a combined signal might look like. I've slapped on some white noise, and it's hard. Like I think everybody in the room kind of knows that it's hard, but this illustrates uh, kind of exactly how hard it can be. Um, so so good. Let's move on with this case study of AU B. I know there's more planets, but let's just say there's only one planet for simplicity's sake. Um, and let's say that we want to conduct follow-up observations on it. So, should I ask for observations once per night for X consecutive nights? Should I try to spread out my observations to like lengthen the baseline? Or should I try to observe in quadrature in intensive bursts? Or I guess observing in quadrature is an example of observing in intensive bursts. And to discern between these different strategies, uh, Megan and Lily and I proposed using the Fisher information. And so uh, this has a few ingredients. So I'll walk through them in this equation here. But at the top level, the Fisher information allows you to quantify how much information a set of measurements contains about some free parameter that you care about. So in our case, the free parameter that we care about is K, the RV semi-amplitude. So uh, yeah, the two main ingredients here are the partial derivative of mu, which is the mean model, which is the Keplerian, with respect to theta m, which is one of four stellar variability hyperparameters that we threw in. And then we also have a inverse covariance matrix, and that's populated by this quasi-periodic kernel that we chose. And so we cook up that kernel with the following ingredients, these thetas, which are the activity signal amplitude, the activity decay time scale, and the stellar rotation period. And then there's also kind of a fudge attribute, the harmonic complexity of the star spot. But this is it. These are the ingredients. So given um, these ingredients and a given time series of RV observations, um, you can produce a Fisher information for that set of observations. So uh, yeah, let's say you've been given 30 observations on NUID. Fantastic. Uh, First thing you got to do is feed in fitted GP model parameters that describe the star's correlated noise. So this will inform our covariance matrix, which we saw in the slide before. And then from tests, we know the transit parameters that we will populate our mean model, our Keplerian with. And so from these, we can basically build a map of different observing strategies. Now, this is kind of overkill. Like, I don't know if we're ever gonna like, you know, observe like 14 days straight and then 13 days off. Like it seems a little bit complicated. But uh, what this map takes a very short amount of time to generate, and that's kind of like the point here. You can try so many like wildly different strategies, and see just visually like, okay, where are like the danger zones and the non-danger zones. And so yeah, on the x-axis, it's number of continuous or consecutive observing nights, and then the y-axis is number of intentional gaps, perhaps, to try to lengthen the baseline if that's something that you want to do. So like at like 10 2, it's like observe 10 nights, take a break for 2 nights, observe 10 nights, take a break for 2 nights until you like exhausted your budget of observations. Yeah, so purple, good, yellow, bad in this color map. And I do not paint points where the baseline takes you beyond an observing semester for NUID. And the reason why it's kind of raggedy, this boundary, is because I've also thrown in custom off nights, and that's something that you can do. Um, I like looked ahead at the calendar when I made this plot, and like there were like proprietary nights that we couldn't like observe on. So like if an observation falls on a proprietary night, then it doesn't to the budget doesn't count. And so that's why sometimes um, a strategy that might look like it takes shorter actually takes longer. Okay. Yeah, great. So that's like a use case, but there are some like general takeaways from our work with Gaspery. So like kind of rules of thumb. And that's so the first one I want to I'll state and then I'll describe the plots, is that planets with orbital periods that are like commensurate with the stellar rotation period or like an integer ratio or multiple thereof will be difficult to disentangle from the stellar signal. And so um, there's nothing you can do about this. Uh, this is just like if nature frowns upon you, then dems the cards. Like so, these are like the horizontal lines on this plot. So this like circus tent plot has observing cadence on the x-axis, and then orbital period of the planet on the y-axis, and it's colored by basically the inverse of the Fisher information content. So um, purple, good, bright, bad. And yeah, this is still for this like AU McB case. And so yeah, these like horizontal lines that I've tried to draw helpful guide red lines on are these like these just like danger zones where and you can see because like they're horizontal, it kind of doesn't matter what your strategy is. It just kind of bad. So this is kind of like a trivially bad case. A non-trivially bad case is you actually live on these circus tents. So these are beat frequencies between the planet orbital and the stellar rotation period, and also sometimes the stellar activity like decay timescale. And these different timescales play together such that like the choice of observing cadence starts to matter a lot. So like, so you like say you know what your orbital period is, so you're fixed on the y-axis and you move along. So there's areas where you're on a circus tent, and there's areas where you're not on a circus tent. And so this type of map helps inform the decisions that you make about to how to craft your observing strategy. And I should say like the phase plot on the right side kind of shows like, okay, these signals are uh, really entangled. And here's an example. Here's an example of where that goes away. So this third case is just an example of a good strategy. So high information content strategy, in which you're away from any kind of beat frequency and away from like those horizontal line danger zones. And yeah, you can see the phase curve shows that the planet signal is um, less entangled, not even entangled in the stellar signal. Okay, so these were all like tutorial like examples to show how one might use gaspery as a way to like, I don't know, sell the gaspery. And then a few months ago, some people actually knocked on my door, metaphorically knocked on my door, and said that they wanted to use gaspery to follow up on three systems. This whole thing is anonymized. Um, but yeah, I just after yeah, I had initial feelings of like, oh, I didn't think I'd get this far. And then I, took Gatsby down from the shelf, dusted it off, and then started using it. And so the first thing was we confirmed in 5 minutes their suspicions that one system was unfeasible, given the stellar activity amplitude and also the stellar activity frequency being very close to the frequency of the planet of interest. So it was very easy to just like check that this was kind of a non-starter. It would take over 100, 100 RVs to get down to the tolerance of 5 K on sigma K. So we can move on. And that was good. That was a good exercise, even if it was, kind of disappointing. Um, but then showing that it worked, they were like, okay, here's two more systems. And so for the second system, with one planet, hold on. There you go. Yeah. So I'll show one proposed strategy. Um, and that's okay. So the dash line is like the minimum observations required to reach that tolerance of 5 K on sigma K. So rightward of that dash line, you're doing better than 5 K on sigma K. Um, yeah, and then the envelope is from bootstrapping 100 times, given our uncertainties on these like stellar hyperparameters, which are sometimes big. Um, yeah, yeah, and the dash line is based off of the median, which is the line inside the envelope. Okay, so basically, if you observe this system once per night, every night, it will take just under 45 observations to reach that tolerance. If you observe once per night, every 2 nights, you will never reach tolerance. Well, at least you won't reach tolerance before 60 observations. And that's a function of the time scales of the stellar activity and the planet's period. And if you observe once every 3 nights, it will take only 25 observations. And so that's already our winner right there. And then, yeah, if you observed every 4 nights, you do a little bit worse. So in the end, we choose our winner, and that's to observe once per night every 3 nights for the system. So yeah, that's like an example of how like a simple one planet system would work in real life. And then they gave me a third system with 3 planets. And the first planet, first of all, is like already kind of a struggle. It's so small that it requires observing twice a night. Like it cannot be done observing like once a night.
Oh, you want me to
Not,
now?
I'm sorry. Oh, sorry.
And just an accidental unmute. Go right ahead.
No worries. Um, yeah. Yeah, in general, having more planets makes it harder to disentangle signals. So, like, expect to have higher minimum observations, these dash lines to be pushed more to the right when you have more planets, because we have to consider these planets jointly. But imagine if you had to do this in like your typical workflow of like forward modeling and injection recovery with GPs, like that that becomes really, really painful. Oh, when you have like multiple planets. And so, okay, so let's show the plots. Click. Okay. Um, so I kind of flew a little close to the sun by also considering like the lower threshold of these envelopes because like I was like, okay, well, the lower envelope means that there is a phase. Oh yeah, I also bootstrapped there like randomizing the phase. Um, And so I was like, okay, so there is a phase, like there's a universe in which we can like do even better than these dash lines, and these are the dotted lines. But I think we decided to be conservative and just um, build the observing strategy off the dash lines. So let's just consider the dash lines for now. In this plot, it might be hard to tell. It was hard for me when I was like practicing this talk. The yellow line is a dotted line. So there's only two dashed lines, green and blue. north of 70 observations. So this is for planet B. This is the planet that requires observing twice a night, no matter what the strategy is. And automatically, like, well, that will be driving the strategy overall, right? Because you can only have one strategy per system. And like what's best for planet C or D, even conditioned on the entire system, is not going to be good for B. So in the end, we chose this the green strategy, observing twice a night every 3 nights. And so it gives you 5K on sigma k for planet B, and then it also gave us approximately 6K on sigma k for planet C and D. So yeah, this is an example of how we used Gaspery in real life. Um, yeah, I'll quickly go over the limitations. We depend on the users knowing their stars very well. You can only do as well as your correlated noise hyperparameters. Although in the era of label transfer, I've been like working on like with the Canon lately, and like if I don't know, maybe you could use the Canon or the Pane to like do label transfer on like some well characterized like correlated noise parameters for some stars that are well studied to like other stars and thereby enable a workflow like Gaspery to be feasible for like many more stars around which like we want to do follow-up. Um, yeah, we also assume that the follow-up will be done by the same instrument that characterized the stellar noise in the first place. So yeah, we don't currently take into account much of the instrument other than like the white noise budget. But because this whole thing, I should say, this whole thing is built on TinyGP and JAX. TinyGP for its flexibility, you can just throw in another kernel to characterize whatever correlated noise you want to throw in for, like, say, the instrument. Um, yeah, and like we've written the software such that that's relatively straightforward to do. And JAX allows auto differentiation, which is very important for calculating the Fisher information. Yeah, we don't take exposure time into account either. So there's some stuff to keep in mind when you're like trying to interpret what it actually means, like what the Fisher information uh, actually means. Um, yeah, I'll leave my conclusions up here, but I also want to just redouble my thanks to Jen for inviting me to give this talk today, and then also say that yeah, as I'm like rounding out my grad school career and applying for jobs in the fall, I've been thinking about things beyond EPRV. Sorry to say this on an EPRV call, but yeah, I care deeply about placing exoplanets in a galactic exoplanet demographics in a galactic context. And then as like Plato launches and Roman launches, I'm really interested in problems um, uh, involving like disentangling the demographics inferences that we get from that, from like what's just being driven by like these disparate stellar samples. So yeah, with that, thank you again for your time. The end.
Excellent. Thank you very much, Chris, for that presentation. Questions from the audience for Chris and about the use of gaspery. I'll lead off by asking if you can say just a little bit more about the idea of label transfer using something like the Canon for stars that we don't have detailed knowledge of their activity from prior RV campaigns, for example.
Yeah. Well, one of the main assumptions of the canon is that there's like this like continuous and one-to-one like relationship between like the spectra. As you vary your spectra, like your labels will vary commensurately. So that's a huge assumption, I think. Um, I This is motivated by current work I'm doing. So I'm visiting the CCA right now to work with Ida Bemard on trying to use the canon to do label transfer for astroseismic ages. And it's like working unreasonably well. The canon kind of scares me, but it's giving me like perhaps unfounded hope that like I don't know, I could like if there's a relationship between the spectra and say like the activity decay time scales, can we do this? And like you can do this for like differences in like resolution. I can do this like between surveys too, which is kind of nuts. So I don't know. I'd like to try. I know Jack Lubin at Know Thy Star talked about doing this for like VSign I as well. Um, I don't know. I think possibilities are like Not endless, but quite big.
Other questions from the audience? And just to check, if folks are interested in using gaspery for their next observing proposal, this is on GitHub, and I know that this is on GitHub, but people can access it.
Yeah, yeah. It's on PyPy, it's on GitHub. I should have put my email. Yeah, but yeah, c.lam@ufl.edu. But yeah, Gaspery is on PyPy and it's on GitHub.
Okay,
Yeah.
excellent. Well, in that case, let's thank Chris again for an excellent presentation. I encourage people to go check out Gaspery when they're thinking about their next observing proposal. And then Hannah, if you're ready, why don't we transition over to you?